Hello everyone. So this is the sixth video of this series, and actually initially I wanted to make only 6 videos, but I think I'll be making a few more videos in this series. I will try to include some more topics like FM frequency modulator and amplitude modulator. So these are some of the more circuits that I am going to include in the upcoming videos. So this is an announcement for now. So this is not the last video of the series, but this is the part 6, and I am going to make a few more videos in the coming days. So in this video I am going to show you how to make a monostable multivibrator and astable multivibrator using 555 timer. So if you don't know the theory of 555 timer, then I request you to please go through one video. I will put the video in the description. This is a very nice video in which the theory of 555 timer is explained in a very nice way. So this is the video. I will put this link in the description so you can watch this video, and whenever if you watch this video, then you will understand like how this 555 timer IC works, and it is explained very nicely with some animations. So please, I request you, please watch this video. If you have not watched this, then please stop this video now and go and watch that video, watch that and come back. Okay, so I hope that you have all watched this video. So here, using 555 timer, we can make actually 3 types of circuits. One is bistable multivibrator, astable multivibrator and monostable multivibrator. So in this particular video I am going to show you how to make astable multivibrator and monostable multivibrator using 555 timer. Okay. So let's first make the astable multivibrator. So I search schematic. So okay, so here I will need the 555 timer. So if I go to this search description search 555, I search. So this is the 555D, which is the part number. Okay. So in this circuit, the astable multivibrator that I am going to make right now. Actually, there is a reason for this. Actually, see, for this monostable multivibrator, we need a trigger input, and in this particular software in PSPICE, we don't have the trigger input available. So we will use the output of this astable multivibrator. We will try to generate this trigger from this astable multivibrator, and we will connect the output of this circuit as an input of this circuit. Okay. 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 So in this circuit, the astable multivibrator, this circuit generates a rectangular wave as output. So I am showing you what it does. But first, let me make the circuit. So we will need a VDC, which is the supply voltage, and we usually use a 10 volt. You can also use 5 volt. Okay. So I connect this to pin number 8, which is VCC, and I use a ground. So we run the biasing. Okay. Now pin number 4 is the reset pin, and when this is 0 volt, it is connected to ground, then the IC gets reset. So we don't want to reset the IC. So what I do is I connect this also to the VCC so that it does not get reset. Okay. So the next thing is next is ground. Again I need the ground. And see, this control pin in 555 timer. So if you go to the theory of this, you will see that if we add some voltage to this control pin, then the timing of the IC gets changed. So we are not going to use this control pin, but it is always important to connect this control pin to the ground through a capacitor. The reason for this is that we know that the capacitor allows AC signal to pass through it. You can use any capacitor here, any small capacitor. So what happens if there is some noise at pin number 5? That noise is bypassed to the ground. So we know that noise has some frequency component. So noise is basically AC signal with some random frequency. So whenever there is some noise in the pin number 5, then that signal is directly bypassed to the ground, and this is why we use this capacitor. Okay. Now in the in the astable multivibrator, the next thing is we short circuit the pin number 2 and pin number 6. So we have to short circuit the pin number 2 and pin number 6. Okay. Pin number 2 and pin number 6 short circuited, and now we need the main circuit part, R and a C capacitor. So this is the basic circuit. Okay, this is the actual circuit, the monostable multivibrator, the astable multivibrator circuit. So this is the basic component of the circuit. So what we do here, we connect this one to the VGC and this one to the ground, this one to the ground, and we connect this point with the pin number 7. Pin number 7, and this point here. So pin number 2 and pin number 6 is sorted, and that is connected to this point between R2 and C, and pin number 7 is connected to the discharge pin. So what happens? This is called discharge. So let me slightly explain you. It is already explained in a very nice way in this video, but I'm also explaining you in a brief way. So what happens? This circuit will generate a rectangular wave. So when this capacitor is charging, okay, so suppose this will be charging from this voltage, this will charge through R1 and R2 through the C. Okay, the C will get charged. As long as this is charging, the charging time depends upon, because it is the path, the charging current will come through R1 and R2. This is the path through which this will charge. So the charging time depends upon R1 and R2 and C. So it is given by 0.693 R1 plus R2 into C, and this is the discharge pin. This is actually connected to ground through a transistor. So you will understand the working when you will see the video. This discharges, when we do to discharge the capacitor, it discharges only through the R2. That means when the capacitor discharges, it will go like this. Current will go like this, and through the discharge pin it will go to ground. So the discharge time depends only upon R2, and it does not depend upon R1. Right? So this is how the circuit works. Now we have to put a load resistance. So I connect the load resistance. So I can connect to ground directly here. Okay, so let's name it RL. And again, this 555 timer is not very useful for high frequency application. So if we put this 1 nanofarad, then again it will be very high. So I make it 1 microfarad. Normally we use microfarad capacitor, the electrolyte capacitors. Although in simulator there is no distinction between electrolyte capacitor and a ceramic capacitor, but in practice normally we use an electrolyte capacitor in this circuit. We can also make it as small as 1 microfarad. So yeah, bigger capacitor can be used to make it as small as 1 second. So let's now do this. So it's a transient analysis, and see, I have not yet calculated the exact on time and off time for this. So I am just showing you some randomly. Okay, so before this saving this, we have to make the transient analysis, and so let's make it for say 10 microsecond and see what happens. And okay, so now we do okay, so we have to save this. Let's name it 555 test 555, and 555.sch. Okay, so this is the output. And if we look at the output, you will see that, okay, so we will first see the voltage. We will see the voltage first. The voltage is voltage across V RL. V RL is to 2. Okay, so I think I have done some mistake here. Okay, this is not microsecond. Okay, this is millisecond, 10 millisecond. Sorry for that. Now it should work. So you see here, if we apply the voltage VRL is to 2, see this is the output we are getting, right? So why we took RL is to 2? Because this is the terminal 2 of RL and this is terminal 1 of RL. So whenever we rotate this like this, this becomes terminal number 2 and this becomes terminal number 1. So we are seeing the voltage at terminal number 2 because terminal number 1 is connected to ground. This will be always 0. Second, what we can see is we can see the voltage across this capacitor, so that you can understand what is actually happening in the capacitor. So if I VC, I think this is C2. So VC2 is to 2, and you can see this. This is the transition period. Let's ignore this part because this is the transition period. If from here it becomes stable, so you can see here the capacitor charges and discharges, charge and discharge, charge and discharge. So when the capacitor is charging, we are getting a high output, and when it is discharging, we are getting a low output, high and low, like this. Okay, so this is how it works. Now I have put some values here, calculated some values here. R1 equal to 2K and R2 equal to 500 ohm. So what is the purpose of this? Because we know that we have to use this particular signal, the output of this particular circuit, to trigger the monostable multivibrator, right? For the monostable multivibrator, we will need a trigger, and this particular circuit, the output of this circuit will act as the trigger, right? So for that purpose, what we have to do? For that purpose, we have to make sure that the on time, because whenever we need a trigger, basically we need a negative pulse, and when we need a negative pulse, I'm showing you briefly. So when we need a negative pulse, the width of this part should be very small. Then only we can say that this is a negative pulse, right? And secondly, whenever the negative pulse is applied to the input of the monostable multivibrator, then the output of the monostable multivibrator will go high and will remain high for some amount of time, and this should come back like this. When it is back to its stable state, this should be back to high. That means the width of that particular signal should be smaller than this. So I'll show you as I'll make this, you will see. So I will make this 2K and I will make this 500 ohm E. So now if I do the simulation, you can see the difference. Again, I am not plotting the current. So see, now this off time of the circuit is significantly small, and this is helpful in the monostable multivibrator. So now I will make the monostable multivibrator and see, you will see exactly how it is helpful. Okay. So for this monostable multivibrator, I am going to use another 555 timer. So let me slightly make this smaller so that the two circuits fit here. So I will need another 555 timer. So the name is 555D. So if you don't remember, you can again search. So this one also we have to connect to the pin number 8 is connected to VCC. The same voltage here connect, and pin number 4 is also connected to this. pin number 4 is connected, and pin number 2 is the trigger, so this will be the output of this. So for example, this one I connect to the output of this. Okay, I'm directly connected to the output, and here also I need some ground. This is the ground, pin number 1, and I have to need a capacitor. I need a capacitor here, and pin number 5 will be connected to this capacitor, just like the previous circuit. Okay, it is connected. Now in this particular case, we are not going to sort pin number 6 and 2, but we are going to sort pin number 6 and 7. So I sort pin number 6 and pin number 7, and I will again need some resistor and capacitor. So this is the resistor and one capacitor here. So this is the capacitor, and this will be connected to ground. This is the ground, and this point has to be connected to VCC, so I can directly connect it to pin number 4 because pin number 4 is already connected to VCC. Okay, so this is connected to pin number 4, so our circuit is done. And this point, the point between this pin R and C, they have to be connected to the pin number 6 and 7. So pin number 6 and 7 are already sorted, so I can draw a wire from here, and it is connected. So this is how it works. Now I have to put the values, so let me just make it, this has to be 500 ohm. You will exactly understand why I am doing this, changing the values, once you see the output. Okay, and again we will need a load resistance. So this is, let's name it RL2, and I connect it here. This has to be connected to ground. Okay, so we have done this. Okay, so this is the circuit. Okay, so let's now slightly zoom in so that you can see the circuit properly. Okay, so this is the circuit. So this is the A-stable multivibrator, and the output of the A-stable multivibrator is used to trigger the monostable multivibrator, and you will see how it helps, like how we set the values of this RC and how it is helpful in this circuit. So first of all, let me plot the voltage across the RL, that means the A-stable part, VRL is to 2, I plot this. Okay, now see, whenever this goes down, this green line, the green line corresponds to the output of the A-stable multivibrator, right? So it is called A-stable because neither of the state is stable. This state is also unstable, so after some time it goes back to this state, and this state is also not unstable, because it does not stay here, it again comes back here. So like this it works. Now I add the trace VRL is to 2, sorry, VRL2. If I apply this, now see, whenever this green line comes down, the red line goes up, right? It remains up for a while. You can see it remains up for a very small amount of time, right? Now if I apply this, so you see now what happens, before this comes down, because this is the unstable state, it remains in the unstable state for a very small amount of time only. Whenever you apply the trigger, it remains in the unstable state for a very small amount of time, and after that time it comes back, and that time is given by T 1.1 RC, right? So we have set R equal to 500 ohm and C equal to 1 microfarad, so 1.1 RC. So for that small amount of time, for around 55 microsecond, 0.55 microsecond or 550 nanosecond, it remains in this small state, in the unstable state, and then it comes back. So if we don't make this, the off time of the A-stable, if we don't make this small, then this will give you some kind of like before this comes up, it will be on again. So let me just show you what happens. So in order to explain this, let me just change these values of the stable multivibrator. So what I do here is that I change this R1 to 2K and R2 to 1K, and C equal to 1. Already this is 2K, but instead of this 500 ohm, I will make this 1K. Now what will happen? This on time will become 2.08 second, and this off time will become 0.693 millisecond. Now earlier this off time was smaller than this on time, but now this off time is 0.693 millisecond, which is greater than this point. This okay. So now there is a mismatch. So let's see what happens. So instead of 500 ohm, I will make it 1K, and the rest everything is same. Rest everything is same. Just I am changing one resistor, and we will run the simulation to see what happens. So I plot this VRL and VRL2. Okay. Now see, we are not getting this exact on time here, right? This should be smaller than this, right? This should be smaller than this. This should be around, because see, this on time is 0.55 millisecond, which is smaller than this on time. But we are not getting that, right? It remains on for a small amount of time, right? It remains on for a longer amount of time. So this calculation is not working, because once it tries to become high or tries to become low again, that is from the unstable state, it goes back to the stable state again. But since this is already since this output or trigger is already in the low state, so it's kind of a loop, right? So we cannot predict this. This on time becomes equal to the off time of this, and sometimes it can be even more worse result. So this is kind of unpredictable situation. So we cannot do this. So this is why I am saying you that this should be always bigger than this. The off time of the stable multivibrator should be greater than less than the on time of the monostable multivibrator, and this is what I wanted to show you. So with this, I hope that you have understood how this circuit works, and you can try different combinations of the resistances and capacitors. So with this, I would like to thank you. So this is the end of this video. Thank you.